Hey everyone, I'm re-recording this after class because the recording I made during class didn't have sound. So let's try again. Here are the different properties of limits. This is a whole bunch of jumble and notation, and don't get too intimidated by it. It's not saying anything too fancy. It's saying things like the limit of the sum is the sum of the limits. And so if you have two different things that you know the limit for, and you want the limit of their sum, then you can just take the limits that you know and add them together. Same thing for multiplication, same thing for division, except you don't want the bottom to be 0. That's bad. Some more pretty obvious properties. More saying that, hey, if there are functions that you can plug in the number and there's no domain problem, then go ahead and plug in the number, and that's going to be the limit. So polynomials, you can plug in the number. If you got something on top and bottom, as long as the bottom's not 0, then you can plug it in. Roots, as long as it exists there, you can plug it in. All the trig functions, as long as it exists there, you can plug it in. All right. Then we'll talk about this, this property. We'll come back to this. But this is talking about limit existing. This is talking about what happens when there's a hole in the graph. We've looked in the graph at what happens, but we're looking at the algebra now. The main tools we're going to use. First off, we're going to try direct substitution. We're going to see, can we just plug in the number? If that doesn't work, and it usually doesn't, the main tool that we're going to have is that we're going to take this idea that I'm about to talk about and be able to get things to cancel so that we can plug in the number. We're going to try and maneuver around so that we can plug in the number. And so let's take a look at what that looks like. The basic idea is that if I want the limit as x approaches 0 of x over x. So take a second and think about what the graph of x over x looks like. Pause right now. What you should realize is that this behaves like y equals 1. Because everywhere except 0, pick any number you like. If I pick negative 20 and I plug that in, I get negative 20 over negative 20, which is 1. If I plug in pi, I get pi over pi, and that's 1. So any number I want, I can plug in and get 1, except 0. So the graph of this function looks like this. It looks like y equals 1 everywhere except at 0, then there's a hole. So because we can say that everywhere except 0, it behaves like y equals 1, and since the limit is interested in what's going on around 0, very close to 0, that means that we can just treat this as x approaches 0. We can just treat this as if we're finding the limit of 1. Canceling out the x on the top and bottom, and finding the limit as x approaches 0 of 1, which is 1. So graph-wise, what's happening is that from the left and from the right, our values are getting closer and closer and closer to 1. As x gets closer and closer to 0, that's what the y values are approaching. Algebra-wise, what's happening is that if I'm looking at anywhere except 0, and we're just looking at points around 0, we're not looking at 0 itself. At any other point aside from 0, this behaves like y equals 1. So since we're just interested in the limit, we're going to treat it like y equals 1. And that's the idea. The idea is that we're going to be able to get things to cancel, and once we cancel, we'll be able to plug in the number. All right, but let's look at some examples where we can plug in the number. All right, for example here, limit as x approaches 0 of x cosine of x. There are no domain problems in x cosine of x. I can plug any number into that. and get something out. So there's not a domain issue, even at 0. I can plug in 0. So if you're able to plug in and get the limit, then you're done. 0 times the cosine of 0. Cosine of 0, don't forget, is 1, but then it's times 0. So 1 times 0 is 0. And we're done. So anytime you can just plug in the number, then that'll be the end of the problem. So pause for a quick minute and see if you can get these next 3. Again, no domain problems here, no domain problems here. If we were to plug in something like -3, then we might be in trouble, or -2. But otherwise, no domain problems there. Here are the answers you should get. So if you can plug in the number and get something out, then that's going to be the limit. But that's boring. So boring that I'm not even going to do these because you just plug it in. Okay, but let's talk about these properties real quick, and then we'll look at some more interesting examples here. Limit as x approaches c if f of x is 2, and limit as x approaches c if g of x is 3. The main idea here is that the limit of the sum is the sum of the limits. So if I want the limit of f of x plus g of x, I can just take the limit that I already know of f of x, 2, plus the limit that I already know of g of x, which is 3, and that's going to equal the limit of the whole thing, which is 5. Another way to say that, if you want a specific function, this is the same as saying that instead of just plugging in the number into x squared plus 3x, I could take and say that this is the same as the limit as x approaches -3 of x squared. I could split up these limits and find them separately and then combine them together. So this is the same as the limit of x squared and the limit of 3x put together. So if you come across some problem where you're having trouble finding the limit combined and plugging in the number combined, then you can just separate out the limits. And so this would be, this is 9, and this limit is -9, and we get 0, the same thing. That's all this is saying. The limit of the sum is the sum of the limits, and you can do it the same way. Same thing over here, as long as the bottom is at 0. Is the bottom 0? No, it's not, then we're good. 2/3 is my limit there. Okay, let's talk about when we can't plug in the number. The most common thing we're going to do, as I talked about, is that we're going to find out what function, what more simplified function it behaves like. And usually that's going to involve getting something to cancel on the top and bottom. So this is the most common way we're going to find a limit other than looking at a graph, which is we're going to factor out of the top and bottom, factor the top, factor the bottom, and see if we can get something to cancel. Because if we can get something to cancel, then that new function that it behaves exactly like, we might be able to just plug that in and into that new function and figure out what the limit is. So this equals the limit as x approaches 5 of x minus 5 over this factors into x minus 5 times x plus 5. Be looking for what you want to cancel. There's an x minus 5 up here. By the way, you should always try and plug in the number first. Let's try and plug in the number. 5 minus 5 is 0. 5 squared is 25 minus 25 is 0. Oh man, it didn't work. Surprise, surprise. Didn't work. So now, what we're going to do is we're going to cancel on top and bottom. And we're going to say that this graph, everywhere except 5, it behaves exactly like the canceled on top and bottom, so 1 over x plus 5. Everywhere else, it behaves exactly like 1 over x plus 5. So now once we have this, we can take it and plug it in. 1 over, plug in 5. That's going to be 1 over 10. So those are the steps. Factor top and bottom, get something to cancel on the top and bottom, and then see if you can plug in the number. Let's try another one. Factor this. Let's see if we remember how to get a difference of cubes. Pause real quick and try this. There's probably going to be an x minus 2 since it was on the bottom. Negative 8. Hopefully you want a remainder of 0 there. So this tells me that it equals, oh wait a second, we didn't try and plug it in first. Let's try and plug it in. Maybe it'll work this time. 2 cubed minus 8 over 2 minus 2. 2 cubed is 8 minus 8 is 0 over 2 minus 2 is 0. Oh no, it didn't work. Thought for sure it would work that time. So we factor the top. This is x minus 2 times, this is my x squared, 1x squared, plus 2x plus 4 on the top limit as x approaches 2 over x minus 2. Cancel. So that means this behaves exactly like x squared plus 2x plus 4. And now that we've gotten those x minus 2's to cancel on top and bottom, we can just plug in 2. 2 squared plus 2 times 2 plus 4. Work that out. 2 squared is 4, and another 4, and another 4 is 12. One nitpicky thing about the notation. This is something I'm going to nitpick. Is you want to keep consistent with your limit notation. Because when we make this canceling move, we cannot say that these two functions are exactly the same. We cannot say that this function is the same as this function, because it's not. This function has got a hole in the graph. So we could say that this function equals this function, because all we did was factor. But as soon as we cancel, we can't say that these two things are the same. So if you do say that they're the same when they're not, you're going to get marked wrong. So the rule of thumb you're going to stick to is keep the limit notation, keep that limit as x approaches 2 notation until you plug in the number. So I kept limit. I tried plugging in the number, so I got rid of the limit notation. Didn't work. So now I factored, kept the limit. Canceled, kept the limit. Plugged in, now I can get rid of the limit and just plug in the number. Next example. Oh, this one will definitely work. Yeah, 0 plus 5 minus the square root of 5 over x. Oh, over x, we're plugging in 0. And so, of course, we're going to get something to work. Square root of 5 minus square root of 5 over 0 is 0 over 0. What a ripoff. It didn't work again. Unbelievable. But we're not out of luck yet, thanks to our friend, the conjugate. The conjugate you probably heard come up, well, when we did problems with square roots, but also when you did problems with I. So think back to when you were simplifying things like this. Maybe 3 plus I over 4 minus I. And you wanted to simplify this to make sure there was no I on the bottom. And the way that we did that was we multiplied top and bottom. Remember, the goal is that all you want left on the top and bottom is a number and an I squared. And so the way that we're going to get that is through a difference of squares. Difference of squares gives us something squared minus something squared. And so all that will be left is the number squared and I squared. So we want to multiply by what's going to make this work out. 4 plus I. And when we do that, we get this nice difference of squares on the bottom. 4 minus I times 4 plus I is 4 squared minus I squared, which I squared is negative 1, so 4 squared is 16 minus a negative 1 is 17 on the bottom. And then we could multiply and expand this out and then simplify the I squared stuff and whatever. This is in algebra 2. The point is that this conjugate is basically the reverse, the same with the addition sign or the same with the subtraction sign, so that I get that difference of squares. So the conjugate we're going to wind up with here is going to happen on the top. I want the top to not have square roots anymore. So I'm going to multiply top and bottom by the conjugate. Square root of x plus 5 plus square root of 5. On top and bottom. And so what that's going to create is, keep our limit, that's going to create, on the top, I'm going to have an x, square root of x plus 5 squared minus the square root of 5 squared over x times square root of x plus 5 plus the square root of 5. So what we're hoping for, don't forget, is for something to cancel on top and bottom. X plus 5 minus 5 is x, and then we still have this stuff on the bottom. And then, by a miracle of the problem was designed so that this would work, x's cancel on top and bottom, which will be the limit as x approaches 0 of 1 on the top and square root of x plus 5 plus the square root 5. Now we can plug in 0. Now plugging in 0 should work out for us. Square root of 0 plus 5 plus the square root of 5. Notice now that I've plugged in the number, I can get rid of the limit notation. But I kept it all the way until I plugged in 0. 1 over square root of 5 plus the square root of 5 equals, this is not square root of 10, this is 2 square root of 5. 1 over 2 square root of 5. And then some people were insisting that that square root get out of the bottom. And so if you want to do that, that would be multiply top and bottom by square root of 5. So we have square root of 5 on top. Then we have 2 times 5 is 10. And that's our limit of that one. So these are our main strategies that we're going to use. Try plugging in the number first. If that doesn't work, try to get things on top and bottom to cancel. All right, we'll finish up these notes tomorrow. I'll talk to you then.